Salam sejahtera and a good day. In this video, we shall be talking about correlation. Correlation shows how strongly two independent and random variables are related to each other, or the degree of association between two variables. This is important as it allows for this relationship to be investigated further for both predictive relationship to be used in regression analysis and further determination of causal relationship if, let's say, the parameters are applicable. But this statistical dependent relationship cannot be used as a sole proof of causal relationship, and therefore the term correlation does not imply causation. I repeat again, correlation does not imply causation. A classical example of correlation is the relationship between height and weight, as they are both independent from each other. However, the correlation between two variables that are not independent from each other are invalid. For example, relationship between height and body mass index, where body mass index is actually a product of weight over height squared. Do remember that there are distinction between the relationship between variable described for correlation versus those of regression. Relationship described by correlation is more retrospective in nature. That means looking back into history at whatever pattern of relationship that has been discovered. Whereas regression, it's more of a predictive relationship. And oftentimes, regression describes the relationship between one dependent variable with one or more independent variables. Correlation can be analyzed using the parametric or non-parametric methods. For example, Pearson's correlation, which is typically used for parametric method for randomly independent variables. Spearman's rule, which is actually a non-parametric equivalent for Pearson's R. Kendall's tau, which is also a non-parametric method for ordered correlation. And phi and Kramer's V for nominal correlation, where phi itself is actually suitable for 2 by 2 table. So the key difference between Spearman and Kendall is that Spearman's can accommodate random distribution of parameters, whereas Kendall allows for ordered correlation. And phi and Kramer basically just allow for us to assign any fixed order based on the name of the parameters itself, hence the name nominal correlation. And the values of correlation ranges from -1 to 1, where -1 denotes perfect negative correlation. That means one variable increases when the other decreases, or 0 denote no correlation. This is actually also the default null hypothesis for correlation tests. And 1 denotes perfect positive correlation, a situation that one variable increases in tandem with the increase in another variable. Correlation strengths based on the correlation efficient can be described and interpreted as follows. When you have a correlation coefficient between 0.8 to 0.99, it indicates a very high degree of correlation. Conversely, if you have a correlation that is between 0 to 0.19, we are talking about an absence of very poor correlationship between two independent variables. And then you can also have a coefficient of between 0.6 to 0.79, which typically denote very high degree of correlation, whereas those between 0.2 and 0.29 indicate poor correlation, and the values in between, which is 0.4 to 0.59, indicate moderate degree of correlation. The correlation coefficient values provided are mostly arbitrary in nature. And of course, different publication or different application will have different values. Be mindful that all correlation coefficients are not statistically significant until proven through further statistical testing, meaning that you will always get a correlation coefficient reading, but it will only be meaningful if the p-value is statistically significant. And therefore, correlation coefficient should only be expressed and used if the p-value is less than 0.05, if you are testing at 95% confidence level. This series of scatter plot represents the correlation coefficient under linear conditions. As you can see here, it ranges from 1, 0 to -1, indicating negative correlation. And this is actually how everything works. The null hypothesis to check for correlationship is actually 0, which means no correlation, as indicated by a straight horizontal line or a random distribution of a scatter plots. This course only covers linear regression, and we shall proceed as such. Correlation can be classified as follows: bivariate correlation, whereby we are describing correlation procedure performed on at least two variables, bivariate. Simple correlation, when correlation is performed only on two random and independent variables, or partial correlation, when correlation is performed on one pair of variables while controlling for the effects of other variables being investigated in multi-correlation model. And of course, finally, multi-correlation, when multiple variables are investigated for their correlation. Analytical methods for correlation may include Pearson's correlation. Pearson's correlation will give us a Pearson's product moment coefficient, or Pearson's R, as indicated in this mathematical equation indicated on this page here. And to allow us to perform Pearson's correlation, the variables must be independent and conform to normal distribution, a very important assumption. And that means it can only be performed on linear data and those conforming to homoscedasticity, similar to what we already described earlier for t-test and ANOVA. So in this case, it is important for us to note that variables are normally distributed. So Pearson's correlation can also be used to summarize the covariance of two variables. And it is actually a summary of this entire formula that allow us to construct a much more elegant and much more advanced form of regression equation when we investigate the regression relationship between two variables. There's also another important property of R as indicated by this Pearson's correlation. And the R, when it's squared, is known as coefficient of determination. Bear in mind that coefficient of determination refers to the amount of variance from a dependent variable that can be explained by an independent variable. So in short, it describes the quantitative relationship between the dependent and its independent variables. And in this case, COD can also be used as a measure of goodness of fit of a mathematical model when you are running analysis of, let's say, a mathematical model based on correlation itself. And bear in mind, in order to utilize the values from COD, the values of parameters should conform to normal distribution. Otherwise, the COD or coefficient of determination will be useless. Further analytical methods for correlation we have included Spearman's rank correlation. This Spearman's rank correlation, the formula rho is indicated here, works on variable regardless of the distribution conformance. And even though it is actually similar to Pearson's procedure, it can take both parametric and non-parametric data. And bear in mind that Spearman's rank correlation, as the name implies, works on ranks rather than absolute values. Spearman's rank correlation is actually something that is being calculated using the formula indicated here, whereby it calculates D, which is the difference between the ranks of corresponding pair of values denoted by their respective xi and yi in a series. And the n will be the number of value in each data set. And bear in mind that when you are performing Spearman's rank correlation, the calculation will only be correct for that series of data, and therefore whatever rank value, rank means, and so on and so forth that we got from this calculation is only valid for that particular set of data and not supposed to be extrapolated to other sets of data unless you are able to determine that the extrapolation conditions are the same. The next analytical methods will be the Kendall's rank order correlation. As the name implies, it works on variable regardless of their distribution conformance, meaning that it is also another non-parametric method, but it works on ordinal ranks, meaning that the ranks should be ordered. For example, we are talking about a sequential order of grade A, grade B, grade C, grade D, grade E, with each of these alphabetical grades lesser in terms of quality as compared to the predecessor one. But having said that, we cannot simply say that 2Bs is actually equivalent to 1A, 2C is equivalent to 1B, and so on and so forth. Even though we know that there are ordered ranks or ordinal ranks, but we do not know the exact, we cannot simply translate the relationship between the ranks, for example, saying 2Bs will equivalent be 1A, and so on and so forth. So in this case, we can use the Kendall's rank order correlation to calculate the correlation coefficient, and as per the Kendall's Tau formula given on this page. This is an example showing correlation in action using a problem excerpted from British Medical Journal published in 2002. In this example, we shall examine the effects of temperature on male births in Europe. Well, first you need to extract the male live birth data from a table for Nordic, Southern, and Central European countries. Use 1 to represent Nordic, 2 to represent Central European countries, and 3 to represent Southern European countries. Analyze the data using both Pearson's and Spearman's correlation. What would be your conclusion? And reanalyze the data again, this time removing Malta. These represent less than 0.01% of the total male births in all European countries. So what is your conclusion? So in order to extract the data, we have to actually copy this data set into Notepad. And from Notepad, we have to transfer to MS Excel and use the find and replace function to remove all spaces between the numbers so that you can get their correct sum. This is actually the example of how we should be doing it. And with this, then we can export all this into SPSS interface. And the SPSS correlation is being performed by clicking Analyze, Correlate by Variate. Put all your variables in the variables section, inclusive of the region classification, with number 1, 2, and 3 as explained earlier. And then, of course, put in male and female. We include the female just for comparison sake. In this particular example here, when all countries are included, we can see that not statistical significant correlation were detected for male and female numbers in relation to increasing temperature, meaning that the temperature has no effects at all on male births. Remember, the female births are actually included for comparison purposes. And there's also one more important thing that you also have to bear in mind. So regardless of whether the correlation is significant or non-significant, there will always be a correlation coefficient. Do remember that this correlation coefficient is only meaningful if the p-value or the significance value is below p less than 0.05, if you are testing at 95% confidence level. So otherwise, do not use the correlation coefficient. Well, once Malta has been removed, as indicated here by removing the coding, which will automatically exclude all correlation data analysis, you can see that there are dramatic changes in the correlation output. While Pearson's correlation still appear to be unaffected by the exclusion of Malta, the data for non-parametric correlations seem to be very significantly affected, to the point that both male and female data showed significant correlationship. So in this case, it is indicating that with increasing temperature, remember we put 1 as Nordic and 3 as Southern European, with increasing temperature, then you can see that there's also a positive correlation coefficient between male births and the temperature itself. And interesting enough, we also see the same thing for females. Well, taking this into context, if let's say we were to examine male births only, this will actually tell us that with increasing temperature, you are going to have increasing male live births as well. But don't forget, since we include the female data as well, so in this case, the female live births has also been increased. So what is the importance of all this finding? So the importance of all these findings showed us that small adjustments, small changes in correlation data will actually yield big changes in the outcome. And therefore, it becomes important for us to actually examine and clean the data properly, justify our data in a correlation analysis in order to avoid misleading outcome or misleading conclusions as such. So this is actually something that further reinforces the fact that correlation does not imply causation. Having concluded the example, having looked at the example just now let's look at another potential misleading example using correlation. We have designed a study to investigate the probable relationship between exposure to cigarette smokes in pregnant mothers, where it is known that high blood cotinine, which is actually a nicotine metabolite, would increase placenta weight and surface area. You tried to correlate the following variables. This is actually part of our original study published in Placenta back in 2002 in collaboration with Hospital Kuala Lumpur and Faculty of Medicine and Health Sciences, University Putra Malaysia. So we have the adjusted placenta weight and the blood nicotine metabolite levels as indicated here. So based on this, we can actually key in the data as per what is being indicated on the pages here. So the correlating variables were keyed into two columns in a side-by-side format, allowing us to determine the relationship between placenta and cotinine. As you can see here, we chose to do by varied correlation, and all the functions are as chosen and activated as per the screen. And it is also important that before we run a correlation, we should investigate our data using the explore function to determine whether it is normally distributed or otherwise. As you can see, procedures illustrated on this page. And based on that, our explore function tells us that the data sets are normally distributed, which is good, meaning that we can use Pearson's correlation. However, it's also indicated that it's actually a relatively large SE, SD, and coefficient of variation were observed. And the box plot for cotinine or nicotine metabolite showed the following. Note the outlier indicated by this particular arrow. Upon further investigation, we found out that this outlier is also present in the indicated scatter plot between nicotine metabolite levels and placenta weight. So it becomes important for us to investigate because the position of this particular data set will determine how many dots or how we position the axis. So similar to the data that I looked for the European population data just now, a small fraction of data could sway how the correlation equation or correlation line cuts through this series of data sets. So based on that, we can see that the correlation coefficient is actually non-significant, indicated by all the values circled in red. So the Pearson's correlation, regardless of significance or non-significant, there will always be a value of correlation coefficient. However, whether this should be taken into account or not very much depend on the two-tailed significance. So in this case, since the p-value is more than 0.05, so even though we have a correlation coefficient, this correlation coefficient or relationship is actually meaningless because it is not statistically significant. So having known that there is actually an outlier, so we excluded the outlier by identifying where the outlier was just now. And after excluding the outlier, which is actually indicated by this particular graph here and here, we notice that the correlation coefficient suddenly becomes statistically significant. And in SPSS, statistically significant correlation coefficient will always be flagged with a star. The more stars that you have, it tells you the more statistically significant it is. So in this case, it is below 0.05, meaning that this correlation coefficient is actually statistically significant at 95% confidence level. And looking at the Pearson's correlation value, coefficient value, it tells us that the correlationship is actually rather strong. So you can see, just by deleting one pair of data, you can actually bring one set of values. We can actually change the correlation coefficient value from non-significant indicated here to significant indicated here. So then we have to ask ourselves one question. By deleting the data, is it cheating? So in this case, you really have to look at your data. Why are there outliers in this case? If you can justify why there are actually outliers, then it will be potentially possible for you to explain and justify your deletion. In fact, as a matter of fact, the offending data is actually data number 7, which gives you the outlier 1.7, resulting in 53 microgram of cotinine. So in this case, by deleting pair number 7, you can actually restore the values of the correlation coefficient to become significant. And since we know that the value based on scientific literature, any value of cotinine beyond 50 is already toxic to the mother and would result in abortion. So This value of 53 is of course not possible under this experiment. So in this case, it is justified for us to delete this particular data, and therefore we end up with the correlation coefficient that is actually significant. So you see, in this case, it's not entirely about deleting the data itself. It's actually what would be the scientific basis that allow us to delete this particular offensive or offending pair of data. So whatever that you do, make sure that you need to have a true or a sound scientific basis to do so. So with that, I guess we can answer that this is actually not really cheating, because it is actually based on science, and therefore it justified for the deletion of data. In this case, the data itself could have resulted from measurements or other technical error.